Hello, everyone, and welcome to this, our latest session of our global webinar series. My name is Wilmer Companion, and I'll be hosting you today. With that, I'll hand it off to Phil, and he'll be discussing some techniques and some guidance for choosing the right polymer capacitor. I know that polymer is somewhat a term that gets used quite a bit in the industry, and polymer capacitors are in some ways one of our flagship product lines and something very near and dear to Phil's heart. So he's put together this presentation to guide us through the spirit of polymer, what it means, what it's for, and how to make the right choices when you're looking at these polymer capacitors. So Phil, with that, I'll hand it off to you, sir.
All right, thank you, Wilmer. So as Wilmer said, today's talk is choosing the right polymer capacitor, guide for the perplexed. So sometimes choosing the right capacitor could feel like navigating a maze. And today I'd like to discuss some information and some tools that will hopefully help you navigate that better and more easily choose the right capacitor. Okay, so let me a little bit about myself before we get started. I'm Phil Lessner. My background is in chemical engineering, but I've spent about 33 years in the electronics industry, 25 of those years being at KEMET. KEMET's Chief Technology Officer, so I'm responsible for product, material, and process development, overlooking that across all of our business groups. Actually, I got my start in polymer capacitors. I was originally hired to develop the Tantalum capacitor polymer product line, which became KO capacitors. So I have really my technical background is in that area. So I hope to impart today some of the things that I've learned over the past 25 years about polymer capacitors to you. So the agenda for today's talk is introduction to polymer capacitors. So I'll talk a little bit about what they are for those who may not be as familiar with that. And then I'll introduce KEMET's polymer capacitor portfolio, which is expanded out to include not just tantalum polymer capacitors, but also aluminum polymer capacitors. Then we'll talk a little bit about polymer capacitor applications and segments. And then I'll dive into the tools that we have and the information that we have for selecting a polymer capacitor. And then I'll finish off with some forward-looking polymer capacitor roadmaps, because since I'm KEMET CTO, it really wouldn't be a presentation without doing a little forward-looking information to you. So let's start out and talk about what is polymer. So polymer, when I talk, polymer can mean many things to different people. But when I talk about polymer in the context of this presentation, and generally when we say polymer at KEMET, we mean intrinsically conducting polymers, which were discovered in the late 1970s by scientists in the US and Japan. And three scientists, Alan Heeger, Hideki Shirakawa, and Alan McDiarmid, won the Nobel Prize in 2000 for the discovery of these materials. These intrinsically conductive polymers have conductivities in between that of insulators and metals, generally in the semiconductor range, and somewhere around, say, 10 to 1,000 Siemens per centimeter. So clearly, much more conductive than insulators and most semiconductors, approaching the conductivity of metal materials. The primary polymer that we use at KEMET and primary polymer used in capacitors is called PDOT, which stands for poly 3,4 ethylene dioxythiophene, so just call it PDOT. It's a lot easier. It was invented by Bayer in the 1980s. I want to point out that this is a pure organic material that contains no metal, So the polymer itself is conductive. That's why we call it an intrinsically conductive polymer. This is as opposed to materials like silver polymer paste, which are a mixture of a metal and a polymer. These intrinsically conductive polymers contain no metal and have a pure organic backbone, which is shown here on the bottom left-hand side of the slide. So why use polymer in capacitors? So, traditionally, let's talk about the tantalum capacitors to start out. So tantalum capacitors were have a tantalum anode, a tantalum pentoxide dielectric, and traditionally the cathode material was manganese dioxide, and then that was overcoated with carbon and silver paste to make contact to the outside world. And the MnO2 cathode served the tantalum industry very well, and still does serve it well in capacitors. And MnO2 is used because it has a self-healing ability. So if there's a defect in the dielectric, the MnO2 is transformed to a non-conductive manganese oxide, which sort of forms a plug in that defect side and causes the capacitor to heal and reduce again back in leakage to near its original specification. An issue with MnO2 is that it's just not that conductive. So in the late 1980s and the early 1990s, after the discovery of these intrinsically conductive polymers, they began to be explored for use in capacitors. So the conductive polymers are about 10 to 100 times more conductive than the MnO2. And like manganese dioxide, they also have a self-healing mechanism, which gives the resulting capacitor high reliability when the conductive polymer is used as a cathode. So since they have higher conductivity than MnO2, the resulting capacitors can have a much lower ESR, which as the speed of electronics has increased, has become an increasingly desirable property. So not only are conductive polymers can be used in tantalum capacitors, but they've also found application in aluminum capacitors, and those aluminum polymer capacitors were released at about the same time as tantalum polymer capacitor. So in an aluminum capacitor, traditionally a wet electrolyte is used as the cathode along with an aluminum current collector. And in the polymer version of the aluminum capacitor, that a wet electrolyte is replaced with a polymer cathode material, which can either have a aluminum current collector like in the wet electrolyte, or can have a carbon and silver contact to the outside world like in the tantalum polymer capacitor. So these aluminum polymer capacitors also have much lower ESR than the wet electrolytics that they replace. So again, ionic electrolytes are actually even a little bit less conductive than MnO2. So the conductive polymers have 2 to 3 orders of magnitude more conductivity than the wet electrolytes that they replace. Also, in the last few years, there's been introduced what's called hybrid aluminum polymer capacitors. So those combine the wet electrolyte and also have the polymer material in them. They have the advantage of having low ESR, but also the very low leakage that you get with wet electrolytic capacitors. And we'll cover all these product forms because KEMET actually has all these products in our portfolio. So just if you look at the polymer in the capacitor landscape, so this shows a plot of voltage versus capacitance for the different types of capacitors. And the major dielectrics are ceramic, film, tantalum, and aluminum. So for capacitors, voltages span the voltages from about 2 volts up to several thousand volts. and capacitances from the picofarad range up into the microfarad and thousands of microfarad range for these dielectrics, where polymer capacitors fit are really in the range of about 2 volts to about 200 volts, and capacitances ranging from a few tens of microfarads to a few 1,000 microfarads. And within this polymer capacitor triangle that I've shown in this diagram, we have the tantalum and aluminum polymer capacitors, which overlap somewhat, but basically fit in that range of a few volts to a few hundred volts, and a few tens of microfarads to a few thousands of microfarads. So if you look at KEMET's polymer capacitor portfolio, it spans the range of tantalum polymer capacitors, aluminum polymer capacitors, and hybrid polymer, aluminum polymer capacitors. And what I've put here is a chart that shows some of the advantages and some of the disadvantages of the different product forms. And really the takeaway from this table is there's no one product that fulfills all the requirements that you might have. So in choosing a polymer capacitor, it's really finding the right compromise between the technical product characteristics of the different product forms, and of course the total cost of the solution that you're aiming for. But this table is really a table to help you get started on sorting out the different advantages and disadvantages of the different products. So for example, if you're looking for a tantalum polymer capacitor, which KEMET sells under the trademarks of KOCap and NeoCap, the advantages there are high cap, low ESR, the potential of having a very low profile product. We have heights that go below 1 millimeter, but the drawback is they tend to be higher cost. For aluminum polymer capacitors, and there are AO-cap, which we also call H-chips. They tend to have less caps than the tantalum polymer, but they're capable of very low ESRs and also available in low profile configurations down to about 1.2 millimeter. Looking at the wound aluminum polymer capacitors, which are available in V-chips and through holes, which we brand as EO-cap. They have medium to high cap. They're also available in some relatively high voltages, where tantalum polymer and the stacked aluminum polymer H-chips are limited to about 75 or 100 volts. The wound aluminum polymers are available to voltages to about 200 to 250 volts. And they can also be a low cost solution, but the drawback is they're generally larger than these other two options. And as we move into the hybrid versions, which have, as I said, the wet electrolyte and also the solid polymer, those, as I said, have the advantages of could be very low leakage compared to some of these other options. And also can have some high temperature versions, but of course, they do have the wet electrolyte, so they're more susceptible to dry out and lifetime issues than the pure solid versions of tantalum and aluminum polymer. And later in the presentation, I'll show you how we have some tools on the KEMET website that you can compare the different types available and actually get some quantitative information on how different characteristics of these different options compare to each other. Let's look at some applications of polymer capacitors. So traditionally, really the first applications of polymer capacitors were DC-DC converter filtering and also decoupling, and really polymers started out their use in really desktop and laptop computers. as input, out, and output, and decoupling capacitors for DC-DC converters, supporting everything from decoupling around the CPU and GPU to memory, I/O, and USB decoupling. So there's a variety of power rails that are needed in these applications, ranging, up to 20 volts on the input, so therefore 25 and 35 volt type capacitors, to low voltages on the CPUs. So CPUs could be generally around the volt. So generally 2 and 2.5 volt capacitors are used around the CPU, to somewhat higher voltages on the peripheral type devices, generally around 6.5 volt rails and 6.3 volt capacitors. Then these polymer capacitors, as the reliability improved and the product offerings expanded out, began to be used in server applications. So some of the output rails are similar. The input rails could be 12 volts, but also there's been a recent move to 48 volt for servers. So that's caused the need for higher voltage input capacitors. So generally for 48 volt input, you use a 63 volt or 75 volt capacitor because of some of the transients that are present on those rails. And then more recently, polymer capacitors have found their way into use into power conversion in industrial and automotive applications. And there, the requirements for lifetime and for harsh environment stability are much greater, and also some of the voltages on the inputs are higher. So we'll take a look at some of the series that we specifically have developed for these applications, which have better lifetime and harsh environment resistance, and also have ratings that reflect some of the higher voltages of the applications, not only on the input, but also for industrial, for some motor applications and other applications on the output of the DC-DC converters. But polymer capacitors are not only for DC-DC conversion, they've also now found their way into other applications. So one application that's emerged in the last several years is power backup in solid state drives, particularly enterprise solid state drives, where the transaction needs to finish even if there's a power failure. So generally there's a bank of polymer capacitors used in these drives. They're often tantalum polymer capacitors chosen for drives that have low profile requirements, and they generally tend to be higher voltages in the 16 to 35 volt range and larger footprints, so they can have tens or hundreds or even thousands of microfarads of capacitance per capacitor, to provide the several milliseconds to hundreds of milliseconds of backup that's required in these applications. Another application is in military systems, military aerospace and defense, which for pulse energy applications. So these polymer capacitors are used for RF pulse energy transmission. So when the transmitter needs to transmit a significant power, they're used to supplement the power supply. So these capacitors could range for use from 28 to 50 volt rails, and therefore 35 to 75 volt capacitors. And polymer capacitors are the capacitor of choice here because of the fairly short pulse times and the fairly quick delivery of the pulse energy that's needed to support these applications. And due to the excellent lifetime and reliability of polymer capacitors, these are now being used for defense and aerospace applications like this. And I'll show in a few slides some of the specific reliability series that we've developed for these applications. And finally, another automotive application besides just DC-DC power supply conversion is the use of polymer capacitors for DC link, and specifically in 48-volt automotive applications. So those are the mild hybrid applications that are especially taking off in Europe and Asia. So here they can be used as a DC link capacitor between the battery and the inverter. And for these applications, high ripple currents and therefore very low ESRs are required, and also good environmental stability, both in a humid environment, but also stability up to 125 or 150 degrees are needed for these applications. And really the hybrid aluminum polymer capacitors are starting to see application in this area. So let's take a look now at some of the resources that we have available at KEMET for choosing between these different polymer capacitor applications. Of course, the place to really start is with data sheets on our website, but sometimes you need more information than you can just get from the data sheet. So we have several online tools that I'll cover that can be used to help choose between the different options. One is Component Edge, which is an online selector for our components, and the other is KSIM, which is actually a SPICE type modeling tool to get detailed electrical parameters. Then, not only have these tools, but we also have a wide selection of technical papers and blog posts that you can use for reference if you want to dive deeper into the information. And I'll show you some links and where you can access those. And then, of course, if you can't get the information that you need completely from the online resources, we have FAEs, sales, and technical product managers that are experts in the application and the characteristics of components that you can always contact us for further information. So I want to go through some of the series that we have and explain sort of the general landscape of what we have in terms of offering for polymer capacitors before diving into some of the online tools. I know if you just go to the go to our website and look at all the data sheets available, it can potentially be a little bit confusing to try to sort through what the different series are, and some of the nomenclature might be a little bit obscure. So I've divided these series into into 3 slides. The first one that I'll cover is general purpose. So we have general purpose polymer capacitors that span our tantalum polymer capacitors, our H-chip stacked aluminum capacitors, and also our wound aluminum capacitors. And these are available in various temperature ratings. From actually 85 degrees C all the way up to 125 degrees C, and various lifetime ratings from 1,000 hours up to 5,000 hours. So you can see we have a tantalum series, we have the H-chip aluminum in a couple of different configurations, and then a wide number of wound aluminum, both in V-chip, which is a surface mount type of wound aluminum, and also through holes that span these various ratings. We also have something called face down, which is a tantalum type surface mount series with the terminals on the bottom, and I'll cover that in a little bit more detail when I get to the roadmap section. But really the takeaway is that face down has better volumetric efficiency, which means you can fit more cap and voltage in a given package. So these tend to be higher CV ratings than the standard series. What I've done is I've made these series clickable. So if you click on the hyperlink here, it'll take you to the data sheet for these given series where you can do a further exploration. We also, as I mentioned, have developed some what I call harsh environment series, specifically really aimed at the automotive and industrial market. So again, we have those available in tantalum, in the H-chip stacked aluminum, and also in the wound type of aluminum, both in solid polymer and also in hybrid. Those come in various flavors, from 105 degrees C rated all the way up to 150 degrees C rated series for our tantalum. And what distinguishes these for the most part from the general purpose is that general purpose tantalum polymer is generally tested to 60 degrees C, 90% RH type of humidity life test. And these harsh environment series are tested at 85 degrees and 85% RH, either for 500 hours for this general purpose, more general purpose T591 series, or to at least 1,000 hours for these AEC Q200 series, which are aimed primarily at automotive applications. And then, as I mentioned, we also have developed a hybrid wet polymer aluminum electrolytic in aluminum. Aluminum polymer, also oriented primarily toward automotive, and those are available in surface mount, in a V-chip, in axial through hole, and also in a radial through hole. And these axial and radial through holes tend to be a higher cap and higher ratings. So they're actually the ones that are intended for high ripple and high cap applications, like the DC link for mild hybrids that I mentioned in the applications section. And again, all these links are clickable, so clicking on any of these series will take you to the data sheet where you can get further information. And then finally, we have a wide variety of what I call special purpose tantalum polymer series that are aimed either at ultra low ESL and ESR type of ratings that are particularly used in decoupling for microprocessors, low leakage series, and also high energy series, which are aimed at applications like the SSD backup, energy backup application that I mentioned, and also this TSP series, which is a stacked series, stacking of several cases on each other in a surface mount configuration, which is found use in some of those RF pulse applications and radar applications that I mentioned. We also have series, HRA series, that are particularly they're available with a guaranteed reliability. So those are our T540 and 541, and then a COT series, T543. So those are available in a guaranteed failure rate configuration. And then we also offer tantalum polymer capacitors in a hermetic seal package, which also have guaranteed reliability ratings, both in a axial leaded configuration, in a surface mount configuration, and also as modules, which can have very high cap and very high voltage. And these hermetic seal, because of their particular construction, are our highest voltage tantalum polymer capacitors, available in individual voltages to 100 volts, and then series parallel configurations in our modules up to 180 volts of rate of voltage rating. So if you're looking for something for military and aerospace applications, this is where you should go to look for an appropriate series. So moving along to tools for further exploration, let's talk about some of our online tools. And the first one is Component Edge. So that's a online selector where you could select the series or components by series, dielectric, capacitance, voltage, or many other parametric factors. So if you go here and you enter the information, it'll come up with components or series or ratings that match what you put in for the parametric. And one of the neat features of Component Edge is that you can also choose to compare different ratings on the by selecting multiple values, and this goes back to when I said the qualitative table that I showed you early in the presentation. Here you can do a quantitative comparison of different types. So here I've compared three 35 volt 47 microfarad ratings to different heights of tantalum polymer along with a wound aluminum polymer, and you can look at the different dimensions and different temperature and ESR ratings to get a quantitative comparison of how the different series compare. Another tool which is really useful is an online electrical simulator that we call KSIM. So there's several things or tools that are under the KSIM banner. The one I'll focus on here is really the one that can compare impedance and ESR and capacitance and inductance, and also ripple current as a function of frequency. So that's also a tool where you can compare different series. So shown here, one of the tantalum polymers and the wound aluminum polymer that I showed on the previous page, and you can look at the impedance and ESR versus frequency. You can also look and find the self-resonant frequency and also other electrical parameters to get a better idea of the detailed electrical performance of these capacitors in the application. If you want to dig deeper, then I highly recommend you visit our KEMET Engineering Center, which is accessible directly or from our website, where we have a large number of technical papers and blog posts. And to make it easier for you, I've listed some of what I think are the most useful ones that dig deeper into the reliability of our different polymer capacitors and also some of the applications of them. So again, these are clickable links. If you click on these links, it'll take you directly to the technical paper or blog post that's listed here. So please check out Engineering Center, which has not only these papers, but also information about all our components, capacitors and inductors and sensors and all the components that KEMET sells. So now I want to cover briefly some of our roadmaps. So we have pretty extensive roadmaps across all our product series, doing CV extensions, ESR and ESL reduction, improving reliability for harsh environments and high reliability applications, and also coming up with new packaging, so new sizes, better efficiency, and new geometry. So if I talked about all of these, this would be more than a webinar in itself. So what I'm going to focus on in today's webinar to close things out are really just two aspects of our roadmap, and that's talking about better packaging efficiency and some new geometries that we'll soon have available. So let's talk about tantalum polymer and packaging. So the trend is to have smaller footprints, lower heights, and the need for higher capacitances One of the issues around the packaging of tantalum polymer is that there's a fair bit of wasted space in the package. So this gray area in the middle is the active element, and the black area around it is really the molding or the encapsulation, which is really space that's not available for the active element. So you can see here from this graph that the volumetric efficiency, or the ratio of active volume to total volume, is only 37% for some of our larger 7.3 by 6.0 surface mount capacitors, and only a quarter of the volume is actually used for the 3528 or 1210 type of tantalum surface mount package. So over the last several years, the KEMET and the industry have worked at improving that. And we've transitioning to what we call the face down packaging, where the lead frame is moved to the bottom of the package instead of surrounding the element. And that allows us to move the end of the element closer to the end of the package, and also the bottom of the capacitor element closer to the bottom of the package. And that can improve the volumetric efficiency from 37% to 54% in the case of the larger footprints, and 25% to 44% in the case of some of the smaller footprints. So we can go from using a third or a quarter of the package to using almost 50% of the package with the face down configuration. But that still means that, you know, half the package is not being used for the active capacitor. So KEMET has now developed something we call KEP, or KEMET Advanced Packaging, where we're using a non-lead frame packaging concept to put the capacitor in the package, and we can improve the volumetric efficiency to almost 3/4 for the larger packages, and almost 2/3 for our smaller packages. So we consider this a breakthrough in polymer packaging. It's actually applicable to both tantalum and aluminum polymer. And how do we do that? Well, instead of using a lead frame and and encapsulating in an epoxy molding compound, we're using an FR4 prepreg material to encapsulate the capacitors along with a copper sheet to make contact to the negative terminal. And when we do this, the configuration looks like this. So we're plating both the negative and the positive end instead of using a lead frame, and we're able to move the capacitor element much closer to the ends of the case using that. And also the FR4, which is of course a common material used in PCB board manufacture, we're able to provide a thinner and uniform wall thickness. And this is the product itself, you know, looks very much like a standard tantalum surface mount capacitor, but it has much more active capacitor volume inside. So with this KEP configuration, we're able to increase the capacitance in the case by about 50% for these larger footprints. And with the smaller 3528 or 1210 footprint, we're able to take a 22 microfarad 25 volt capacitor and take it from a 2 millimeter height to about a 1.2 millimeter height capacitor, therefore downsizing the height. So when is this new series going to be available? Well, we're scaling up right now, and we intend to have engineering samples available in the first half of next calendar year, and then be in mass production in the second half of calendar year 22. Then I'll finish off by talking about some advances in aluminum polymer capacitor packaging. So traditionally, as I think everybody knows, aluminum capacitors are around, whether they're polymer or wet electrolytics. And if you're placing multiple aluminum capacitors, that can result in having to do a lot of placements, wasted space in between the capacitors. And since there's a lot of airspace in there, the heat transfer isn't the best. So KEMET has developed a rectangular form factor aluminum capacitor that can be the solution to overcome some of these issues with multiple round aluminum capacitors. So if you look at our current offering, it's available from 1 millimeter up to about 20 millimeters in various configurations. And with the flat aluminum rectangular capacitors, we're intending to offer that from about 1 millimeter up to about 8 millimeters. So we have actually 3 different series we'll offer. The PPC at 1 millimeter, the ULT series at 2 millimeters and 3 millimeters, and then the ALL series that has an 8 millimeter. They'll be offered in various voltage ratings and some fairly high cap ratings at different temperature ratings, again, suitable for replacing multiple individual surface mount capacitors and also suitable for stacking in modules. The ALL series and PPC series are sampling now and will be available in production this year and next year. And then the ULT series, which is actually intended to be a surface mount series, will be available for sampling next year and then production in calendar year 23. So I want to leave you with really 3 thoughts. First, KEMET has a complete portfolio of polymer capacitors, which spans tantalum polymer, H-chip and V-chip and through-hole aluminum polymer, and then the hybrid aluminum polymer series. So we have really, I think, the most extensive offering of polymer capacitors out there in the industry, and they're expanding it all the time. Choosing the right polymer capacitor depends on many technical factors and total solution costs, and KEMET has both technical collateral and tools like KSIM and Component Edge that can help with the selection. So hopefully I've shown you some of those tools, and you can go click the links in the presentation and go right to the website where those where that collateral and tools are located. And then we have a robust roadmap for new products really across all our polymer product lines. We're always developing new ratings and new geometries and new capabilities in terms of capacitance, voltage, and ESR. So please do continue to visit our website and follow us to get the latest updates on that. And you can actually follow me on social media. I'm on LinkedIn, I'm on Twitter, and I can be contacted by email and by phone if you have any further questions. So with that, thank you for listening to my presentation, and I'll turn it back to Wilmer for any questions.
All right. Yeah, thanks, Phil. There's definitely no shortage of ways of getting a hold of you. All right, so yeah, we do have a number of questions, and we'll try to get through these sort of in rapid fire succession. So the first one, Phil, is that I'll sort of summarize it a little bit, but it's in essence trying to compare the cost between AO and KO. This particular person quickly did a search for a 220 mic 6.3 volt KO that, according to DigiKey pricing, is more expensive in the aluminum sort of format than the tantalum format. So can you make any comments as to sort of the relative price comparison between an AO technology and a KO technology?
Yeah, I mean, it really depends on the rating. So I can't give, very specific guidance, but generally, tantalum will tend to be more expensive, but you can also, get more cap and voltage in a given case. So I think you really, what you really need to look is at the total cost of the solution, especially if you need to place multiple capacitors, which solution is going to give you the lowest overall total cost, which is of course the cost of each piece multiplied by the number of pieces that your solution needs.
Yeah, yeah, it's definitely there's no hard and fast answer for it, and I have noticed that myself also, that sometimes part to part comparisons changes, but then when you, as you said, apply the total cost of the solution, it definitely affects the price. Then following on through is what limits the voltage rating, the voltage carrying capability of conductive polymer? Are there any plans to get into the hundreds of volts, 400s, or 630s compared to what's available in ceramic and film and electrolytics?
Yeah, so that's a good question. So tantalum polymer is limited by the stability of the dielectric as you form to high voltages. So tantalum polymer is probably always going to be limited to around 100 or maybe 125 volts. With aluminum polymer, there's the capability to do much higher voltages. Obviously wet electrolytics are available to 450 volts, and KEMET even has some wet electrolytics now that are 630 volts. We already have aluminum polymer available to 250 volts, and part of our roadmap, which due to time I wasn't able to go over today, we have development so that we can get to at least 400 volts for aluminum polymer. So look for 400 volts. In our future, we might be able to go beyond that. That really depends on adjusting the chemistry so we can get the breakdown voltages for those higher voltage ratings. So for aluminum, it's not limited by the dielectric; it's more limited by the voltage achieving the voltage breakdown using the right chemistry.
All right. So I'll go through the next one here pretty quick. And do you have any comments on derating guidance for KO-Cap, particularly as it pertains to harsh environment?
Yeah, so generally we say for the lower voltages, you can use them at 90% of the rated voltage, and I believe above 16 volts, we recommend 80% of the rated voltage. For the harsh environment series, those we've developed, some higher voltage ratings. I know people would want to potentially derate those more in their applications. I mean, you can use them according to the 80 and 90% rule, but we have some higher voltage and higher cap ratings that you can use at higher deratings.
All right. So one of our favorite topics, hermetically sealed capacitors are the new through-hole hybrid polymers hermetically sealed? Or can you comment a little bit, Phil, about some of our hermetically sealed options, leaded and surface mount?
Right. So the only true hermetic seal capacitors we have are the Tantalum hermetic seal capacitors, are T550 and 551 series. Those are truly, hermetically sealed with a glass to metal seal. The aluminum hybrid capacitors are not hermetically sealed. They have a rubber gasket, like most all aluminum capacitors. So they do to allow any gas that's generated during operation to escape. So the answer is no. The aluminum ones are not hermetically sealed. Just the tantalum hermetic sealed series.
And does that include the surface mount ones, the 555 and 556?
Yes, that includes. So yes, we have 550 and 551, which are leaded, and the 555 and 556 are also hermetically sealed.
All right. So this should be a quick one. So what's the significance of the epoxy color, Phil, the yellow and the black that we have? There's lots of stories with that.
Yeah, so traditionally tantalum, KEMET's tantalum was yellow, and as we introduced polymer, there were more and more requests for black. So most of our polymer series are black. but some of the high reliability series are yellow. So there's no, so the quick answer from the technical standpoint is there's no technical difference between the yellow and the black. It's just a color that identifies, some series versus other series.
So I'll try to summarize this next question and expand on it a little bit, Phil. So the question is about different types of polymers for polymer capacitors. So when we say polymer throughout our product lineup, do we always mean PDOT?
For our products right now, we always mean PDOT, but there's actually several different types of PDOT. There's a type where you synthesize the polymer, what we call in situ, and then there's a type that is pre-polymerized, and depending on the voltage and some of the other characteristics of the capacitor, we may use one or both of these. This could be probably a 1 or 2 hour seminar in itself, and we've actually given some talks on that, and I'd be glad to give references to the literature where we've discussed that. So choosing the right chemistry is fairly complicated, and we put a fair amount of time into doing that. Right now, all our chemistry is PDOT, but we're always experimenting with other chemistries. So in the future, it could include other conductive polymers.
Okay. Then this next one, another sort of summarizing a bit. Can you comment a little bit, or do we have any literature, Phil, on anomalous charge current for polymer tantalum capacitors? I know that was a thing that we were sort of very carefully treading around for the last few years, but I think it's well known enough now that yeah. So
yes, we do. We do have literature. I believe there's a white paper. I'm not sure whether it's on Engineering Center, but I know it's available. We were actually the first ones to publish on this phenomena. And we have a journal article that was published in the Journal of Electrochemical Society, going into some fair bit of depth on the technical and mechanistic phenomena, behind it. So, we can make that literature available to anybody who's interested.
All right. Then, Phil, as you know, the world of ceramics is all about getting smaller in size, or for many types of applications of ceramics, it's all about getting, smaller in size, 0201, 01005. What about plans for downsizing in KO and AO?
Yeah, so right now in AO, we don't have plans for downsizing, but we can. In KO, let me go back here. So the series where we have the smallest case sizes are this FPS and GPS series. So the GPS series is available down to 0805 case size. And we could do 0603s if we choose to. The other thing is not only downsizing in terms of footprint, but also downsizing in terms of height, which is something that's really desired by a lot of our customers. So we have products available in these series down to 0.8 millimeters in height, and we have some development work undergoing down to 0.5 and 0.6 millimeters in height. So definitely, going down in height, going down in footprint. Whether we introduce anything smaller in terms of footprint, like 0402, really depends on demand from our customers. That's really an area where I think ceramic sweet spot is, but if there's specific applications for tantalum polymer that makes sense, then we'd certainly consider that.
Thank you, Phil. All right, we got about 3 or 4 more questions before we're already sort of over our originally allotted time, but we might as well just try to wrap these up in the next 5 minutes. Definitely particular because we have some good ones here. Phil, as far as our AEC-Q200 qualified ones, the T598, 599, any issues in long-term storage in extreme conditions, extreme dry or extreme humid?
Well, as I said, the AEC Q200 series, we've tested to 1,000 hours for 85, and actually, that's what we put in our data sheet. Some of these have been actually tested to 2,000 hours for 85, and that's a pretty harsh condition. We've developed some conversion between that and what it means at sort of less harsh conditions, and so we're expecting under sort of normal use condition that these can last a very long time under humid conditions. Dry shouldn't be dry heat shouldn't be an issue for these capacitors within the lifetimes that they're capable of. And again, we have some guidance in our data sheets of how, let's say, a 2,000 hours at 125 degrees would translate to a particular mission profile for let's say, an automotive application. So you can look at the data sheet to try to get a handle on that, or you can contact one of our FAEs or technical product managers to get a lot more information about that topic.
All right, thanks, Phil. Can you compare the reliability between polymer and MnO2?
Yeah, so from both polymer and MnO2 are very reliable. And we've done extensive accelerated testing on the polymer and shown that they're just as reliable as MnO2, and in some cases, in some ratings, actually more reliable. I think where MnO2's niche is these days is really at higher temperatures. So polymers, do degrade over time at higher temperatures. So if you're looking for a rating or for an application where you need like 175 or 200 or 230 degrees, then MnO2 is certainly the capacitor of choice. But for normal sort of applications and even for harsh environment conditions in automotive, polymer capacitors are just as reliable as MnO2, and for some of the higher voltage ratings, I would say even more reliable.
Yeah, we've entered the reliability portion of the Q&A session. So is the expected lifetime for polymers when it comes to temperature and ripple current similar to that of wet electrolytes?
Yes, it depends on the wet electrolytic. So by wet electrolytes, if you mean wet tantalum type of capacitors, then our polymer Herm seals are just as reliable as the hermetically sealed wet tantalums, and they have advantages of better cap stability with temperature and better and certainly better ESR. So it really depends on the particular wet electrolytic system that you're looking at. If you're comparing aluminum wet electrolytics to aluminum polymer, then polymer can definitely have some advantages in terms of lifetime. Because there's no dry out mechanism, unlike the wet electrolytics.
All right. Cool. Well, that's it. I think we got through everything. If we missed anything, then I'm sorry. But of course, either I'm available or Phil is available for some follow-up later. And with that, we'll close it out. Thank you, Phil, for your presentation. Definitely highly engaging and high level of interest here. As we close out, you'll be receiving a link inviting you to take a brief survey to help us improve how we proceed and deliver this type of information or webinars to you. Please take some time to complete that survey, and then check out our calendar on Engineering Center for some more upcoming webinars. So with that, thank you, Phil, and thanks everybody for attending.
Yeah, thank you. Bye-bye.